Good day to Dr. Aminu and Dr. Jeevan. I am Shikai and this video aims to give you an overview on my FYP, which is the study of process parameters and short channel effects in GAA nanowire FET. GAA NWFET stands for Gate All-Around Nanowire Field Effect Transistor. Nanowire has a width less than 10 nanometer. The channel can be in cylindrical or square cross-sections form where the gate surrounds the channel in 360 degrees. It is a promising configuration for better short channel behavior and gate controllability over the conductivity. Downscaling of transistor causes several short channel effects such as degrading subthreshold swing and increasing drain-induced barrier lowering. Reduction of gate oxide thickness causes leakage current due to tunneling, thus leading to a high power consumption and low device reliability. Here comes out to my first objective: to analyze short channel effects by varying geometrical and material parameters on the performances of GAA nanowire FET such that the device will achieve the minimum subthreshold swing of 70 mW per decade and maximum DIBL of 130 mW per watt. According to Samsung Electronics, GAA nanowire FET architecture allows up to 35% decrease in area, 50% decrease in power consumption and 30% improve in performance. This comes out to my second objective: to optimize GAA nanowire FET by combining the best geometrical and material parameters which will produce low threshold voltage and high current ratio in the range of 10 to the power of 3 to 10 to the power of 12 by using Takuji method. For research methodology, research papers on GAA nanowire FET are studied to identify the parameters and method used in device optimization. Next, the device is modeled and simulated by using COMSOL multiphysics. Geometrical and material parameters are varied and simulated. The simulation results obtained are then analyzed and benchmarked against the existing research papers. Lastly, Takuji method is used to optimize the device for high current ratio and low threshold voltage performances. The results and discussion will be separated into two parts, where we will first look into the variation on different process parameters. The process parameters involved are gate length, channel width, nanowire materials, gate oxide materials, and high K coverage angles. The figure on the right shows the model of GAA nanowire FET. Firstly, gate length is varied in the range of 2.5 to 4 nanometer. The results are benchmarked against the work done by Sharma and Kumar in 2017. When the gate length decreases, threshold voltage will decrease as less amount of gate voltage is required to form the inversion layer due to shorter distance between source and drain regions. Current ratio reduces exponentially with gate length, causing low drive current, which can be seen in the blue line, and high leakage current, which is reflected on the red line. Thus, it is harder to switch off the device completely. Downscaling of gate length causes high SS and DIBL. Due to DIBL effect, the gate is ineffective and has low controllability on the channel region due to electrostatic decoupling between source and drain regions. Next, channel width is varied in the range of 3 to 3.6 nanometer. From equations 4.1, drain current is directly proportional to channel width, which matches with the transfer characteristic graph. When the channel width of GAA nanowire FET decreases, threshold voltage and current ratio increases, while leakage current, SS and DIBL decreases. The subband energies increase, leading to higher potential barrier, lower leakage current and higher current ratio. Next, nanowire materials of GAA FET are varied among silicon, germanium and indium phosphide. Conductivity of nanowire is affected by the electron mobility of the materials used. From equation 4.3, electron drift velocity is directly proportional to electron mobility. Therefore, GAA nanowire FET with indium phosphide has the highest drain current since it has the highest electron mobility as presented in the table on the right. However, the drawback associated with indium phosphide is the high leakage current with even at low gate voltages. This would mean high power consumption when the device is in off state, but it will perform better than silicon and germanium in high voltage applications. Next, gate oxide materials of GAA nanowire FET are varied among silicon dioxide, silicon nitride, aluminium oxide, and hafnium oxide. Threshold voltage is almost constant with a difference of 0.01 volts since all the gate oxide materials have the same total gate capacitance by applying the EOT. EOT of high K dielectric materials can be calculated by using equations 4.5. It implies the thickness of high K dielectric materials necessary to achieve the total gate capacitance as with the silicon dioxide. From the results obtained, hafnium oxide, which has the highest dielectric constant, shows improved current ratio, leakage current, SS, and DIBL as compared to silicon dioxide. Thus, hafnium oxide is the best suited gate oxide materials of GAA nanowire FET. Next, the high K dielectric materials hafnium oxide coverage on the gate oxide over the China region is being varied in the range of 0 to 270 degrees. The results are benchmarked against the work done by Kabale et al. In 2020. As the high K coverage angle increases, the current ratio increases as well. This is due to better gate electrostatic control over the China region in GAA nanowire FET with high K dielectric material, which can reduce off current at low gate voltages and enhance on current at high gate biases. At high K coverage angle, the results obtained in sub-threshold swing is very close to the ideal value of 70 mW per decade. In parameters optimization, Takuji method is being used. It is a systematic technique to investigate the combined effect of multiple factors with regards to the device performances. It uses conceptual signal-to-noise ratio approach as the quality characteristic of choice and Pareto ANOVA to determine the percent contribution of each factor. In this work, the standard orthogonal array is being used for 3 factors at 3 levels with 27 experimental runs as presented in the table. In order to achieve high current ratio and low threshold voltage performances, the larger the better characteristic is applied on the current ratio, while the smaller the better characteristic is applied on the threshold voltage. Based on the results obtained from Takuji method, it is found that nanowire material imposes the largest effect in the device performance, followed by channel width and gate length. The device is simulated by using 2 sets of optimized parameters. Referring to the optimized case for high current ratio performance, the results obtained are compared with the base case. Threshold voltage and current ratio are successfully improved by 0.67% and 40.85% respectively. Referring to the optimized case for low threshold voltage performance, threshold voltage are successfully improved by 98.43%, but current ratio is degraded by 99.85%. The results indicate that there is a trade-off between threshold voltage and current ratio. In conclusion, the desired parameters for GAA nanowire FET optimizations are tabulated for high current ratio and low threshold voltage respectively. It is found that nanowire material is the dominant factor for device performance. It is highly recommended for future work to be conducted to improve the device performances with other considerations such as doping concentration and device structure. Moreover, it is crucial to study the impact of deep level traps in nanowire as it will affect the conductivity and efficiency of device. Lastly, the environmental impact of this work is being evaluated. In Malaysia, electricity is mainly generated by the combustion of fossil fuels which will release greenhouse gases. By lowering the power consumption per device through GAA nanowire FET, we can reduce the usage of electricity to protect the Mother Earth and promote the awareness of conserving natural resources at the same time. For societal impact, consumers need to pay less electricity bills by lowering the power consumption per device through GAA nanowire FET. It also allows advanced technological applications that improve the quality of life. Due to the unique one-dimensional structure with remarkable optical properties, nanowire provides the opportunities to the development of high-efficiency photovoltaic devices. That's all for my presentation. Thank you for your time and see you during the Q&A session.